haven't gotten to grade yet. The midterms. And my terrifying Halloween. I think it'll be okay. Look a little bit. So a little bit behind, but I'll hopefully by Wednesday I'll have the homeworks I did last week. So I mean, well, I'll talk to you about it. So today we want to continue talking about rings, and I wanted to, well, share with you some of the things that one of the reasons I find them so interesting to study. And that's maybe illustrated well by looking at some really basic questions, maybe that I don't know if you've ever thought about, but I think kind of fun. So look at solutions, so-called Fermat curves. Sorry. Solutions to the equation x to the n plus y to the n equals 1. Anyone know this Fermat's last name? Like the story here. Kale's okay, so for those that don't, there's a really amazing story. Long story. When I was a kid, I was your age. There was a conjecture, and everyone was conjectures, unsolved, unproven or disproven state. Said that that there are no integers, that if n is greater than n is greater than 2, there are no integer solutions. Except for like the stupid ones, like x or something like that. And then I got some there. So like no non-trivial integer solutions. This is called Fermat's last theorem. And Fermat was a lawyer. I'm say like 16. And he wrote apparently in the margins of one of his law books that he had this beautiful proof of this theorem, but that the margins were too small. Take a proof. Classic student statement. Sorry. It stayed open until I was a kid. People thought they'd proven it many, many times. All these proofs were found to be correct. And then when I was probably around your age, a little younger, Brad Princeton proved it. Well, actually, he announced the proof on air. But the error was fixable, unlike previous proofs. There was like some other people worked on it with them. They fixed the error. This was like hundreds of years of the problem. So this is a huge deal at the time for math. But one way of looking at this problem is to look at this curve and ask for rational solutions for x and y, for numbers that are rational. Multiply by a common denominator and get a solution to this equation. And of course, if n is 2, you know what this equation looks like over R. You get circle. However, I don't know if people ever looked at the n equaling 3 or higher cases, what those look like. I mean, I know people look at them. I don't know if you guys have ever looked at this. You put it into, graphing calculator or will be something kind of like this. Or like that. And as you go up, n equaling 4 goes back into something like a circle, but it looks more like kind of a square. And as the numbers go up, these two prototypes kind of are the ones you get. So when it's odd, you get something like this, except you get a sharper kind of, it approaches something that looks like almost like an absolute value at some point, and then just kind of the straight line, you know, like this negative x. And then here it actually approaches a square. So what this has to do with Fermat's theorem is kind of a deep thing. And you may be kind of bored when you look at this pattern and be like, okay, I can see that. Not much interesting going on there. You'd be right, at least from a pictorial point. However, you can, so if you look at this, what you're looking at is you're looking at function, you know, you're looking at the space whose ring of functions is in fact this quotient ring. This quotient. However, once you learn a little bit of classical algebra, know that the best field to work over, not the reals, but the complex numbers. That's much better. Algebra, it's great field, but the best field around. But you can ask for, what are the solutions to this look like? Okay, well, you have an equation in a complex, a two-dimensional complex space, which is, well, if you think of complex numbers as being two real dimensions, this is a four-dimensional space. So the solutions to this equation will be a pair of complex numbers inside of C2. Solutions. It's people, what do people think? What do you think the dimension of the space of solutions is? A guess. 4. So the ambient space, meaning the space in which this thing lives, is C2, which is 4. Now let's look at the analog here. This lives, these pictures, these graphs I'm drawing for you guys, they're graphs of an implicit function inside of R2, right? These are all in the plane, R2. And their graphs are one dimensional, right? If I take this, like the graph of these guys, these are one dimensional things inside of two-dimensional plane. The dimension of this guy, the space of this, solutions to this, is one-dimensional inside of two-dimensional space. So what about here? Here we have an ambient four-dimensional space. What do you think the dimension of the space of solution is? Think of it. Not 4. 5? Okay, so this, hold on. So there's the ambient space, and then there's the subspace. We go to a subspace, the dimension should either not change or drop. So here we have an ambient space, that's dimension 2, the plane. The set of solutions to this equation is dimension 1 in these cases. It's a curve. But here, our ambient space is dimension 4. The dimension of the space of solutions to the same equation, but now in complex numbers. Drop. What do you think? How much do you think it should drop by? 2. Very good. two real dimensions, or one complex. So the one constraint here drops you down by one real dimension here, and it'll drop you down by one complex dimension here. So if you go to 2 minus 1, that's 1. But now we are a complex dimension, so that's 2. So the set of solutions to this equation is going to be 2n dimensional. 2n minus 1 dimensional. So what am I talking about? 2 dimensional. 2 dimensional. I was thinking of something else. Okay. 2 dimensional. So there's surfaces. Okay, big deal. What does n equal 2 look like? Well, here we can do a little algebra, which we couldn't do for Pythagoras or for R. We can realize that this is actually, we can factor x squared plus y squared with the complex numbers. We can do this in the reals, but we can't. If we factor it, we can then do a change of variables. Call this u, call this v, and we can say that this is isomorphic to the ring we'll see a little later in this week, CUV over UV minus 1. But this relation UV minus 1 is just saying that V is the inverse of U. In other words, you're looking at solutions, pairs of complex numbers where one has an inverse. These are all non-zero complex numbers. Solutions are what are called C star. They're all non-zero. This is the silly surface of just the plane, complex numbers, real, hard to use dimensions. So complex plane, which is just ordinary plane minus the origin. So it's a punctured plane. 2. It's all 2. Ring. Equaling 3. This is the picture in the reals. Equaling 3. Surface. What do people guess? Any guesses? This is sort of the first problem with Fermat's last theorem. It's trying to solve that one. First time when we had was actually solved a long time. Guesses to what this surface is? It's like extremely, very happy as a young man when I like this. It's just like, oh my goodness. But n equaling 3, if the surface is a torus minus 3 points. Very symmetric torus actually as well. That doesn't look like this. It looks different. When you go to n equaling 4, it becomes like one of these sort of like glazed donuts, but it's got several holes in it. In fact, the number of holes then you can predict d minus d, sorry, maybe n minus 1 times n plus 2. 2. N minus 1 times 2. Would be the number of holes. So it's sort of the complex, and there's going to be some punctures here as well. You can get rid of the punctures. So this is like we're out. So what all of a sudden happens when you start studying these things is you look at these very innocuous equations. Very like this is just the equation for the unit circle, but now you're just changing the exponent slightly, increasing it. And you look in the right space, and all of a sudden you get these very interesting subspaces. And if you want to study what happens when you study these equations and we study these rings, is you're really studying these spaces. And you can start really getting some interesting results. This case, n equaling 3, well, you can change this polynomial to be more complex, more interesting. And you'll get a whole bunch of different tori that have different structures. These are called elliptic curves. And there are, I can comfortably say, hundreds of books written. This was sort of underlying the proof of Fermat's last theorem, the study of elliptic curves. Elliptic curves are really important. Okay. Anyway, I want to introduce you to that. I was going to talk a little bit about tropicalization and Feynman diagrams and string theory, but I think I'm going to probably, I think I might take this a little too far out there. But the truth is like there's some really elementary things you can do to sort of understand why these are the shapes that you get. And they do feed into a little bit of physics, different methods that aren't hard to understand, but have to do with sort of particle physics. Anyway. Okay. That's just hopefully going to pique your interest a little bit. But now I want to get back to sort of some of the more basic stuff and studying these rings, and studying rings in general. So and for that we have 11. We're on 11.5. Last week we finished about around 11.4, and this has to do with adjoining elements, which I've sort of mentioned a few times as to why we're studying polynomial algebras. But let me try to explain it a little bit more here. So suppose we have a ring R. R is a ring. And it's not any ring. Let's say it's a subring of another one, ring R prime. And alpha is an element of R prime. Then we can consider the ring R of alpha, so write R of alpha, be the smallest subring of R, containing both, of R prime, containing both R and the alpha. So one thing you can see is that, in fact, all of the elements of R of alpha can be written as just polynomial expansions of alpha with coefficients in R. So this is going to equal the set of all things that look like this, like C not, let's see, 1 alpha. It's like a polynomial. Alpha, here are the coefficients, these are all in ring R. However, this is not a polynomial ring. It's not isomorphic to polynomial ring because there may be some relations. In other words, we may have chosen alpha to be just an element of R in the first place. Then sure I can write things this way, but I get a lot of redundancy. The one thing we do, so for example, you can look at the rings, take Z contained in R. And then we can look at something like, so we consider square root of 2. This is something that are usually written as z plus, without the circle, I don't know, plus z. But these are the same thing. And anything, sure, I can write things. I could write, 4. I could write 4 here. Write 4 in here. That's an element of here. And so is square root of 2 squared. But they're equal. So I'm just saying, yes, it's true that everything can be written as a polynomial of alpha, but it may not be uniquely written. So this is adjoining an element to R when R is a subring of another ring. That element is in that other ring. However, one thing we often want to do is we want to create new rings. Right? We don't want to have to rely on the existence of something that we don't have access to. We want to create that. And so indeed we can do that. And that's done through using polynomial algebras. So you can also abstractly join element alpha. Well, okay, what is alpha? It's some abstract element that satisfies a set of relations. They say we have a list of relations, f1 of alpha, polynomial relations, up to f sub k. Polynomials f alpha, or f sub alpha. The way we do this is we just take the polynomial algebra. This is accomplished, this is done by considering polynomial algebra R of x, and then modding out by the ideal generated by these polynomials. 1 of x. Modding out sort of sets all of these equal to 0. So when we set all of them equal to 0, what we're doing is we're forcing this relation, all of these relations here. And now the alpha that we're looking for is precisely the class of x. It's the congruence class of x in this quotient ring. Here. Alpha. Let's see. Just write x bar. We're in a quotient ring. We're taking that. So if we were to do the previous example, but now do it abstractly. So here we have the integers as a subring, the reals. But let's say we didn't even know about the reals. And algebraically, we wanted to have some square root of 2. Then all we need to do is we can just take the integers and say, well, we want something whose square is equal to 2. So we want x squared minus 2 to equal 0. Quotient out by that polynomial, or at least the ideal generated by that. This will be isomorphic as a ring to this c square root. So we don't really need this. We don't need these real numbers, at least for this purpose. We can define this ring without. Questions? Make sense? Okay, so there's a proposition, proof proposition. By the way, there's, for those that story, which wasn't a very good story because there wasn't too much. I mean, there's kind of nice historical. There are not a lot, but there are a few big conjectures like that still available. Like there's these conjectures that are sitting there out, like Millennium Prize conjectures that have not been proven, that are wide open and have like dollars attached to them. So, want to like undergraduate research project? Probably not. But there's a lot of wonderful math around some of them. Okay. So this is proposition from the book 11.5. So that part be a ring. F of x monopolynomial. Okay, so as I just mentioned, we're going to define this ring. Let R alpha note ring, abstract ring, abstract quotient, R of x, F of x, one relation here, obtained by joining alpha satisfying this relation. What can we say about this ring? What can we say about it? Well, okay, so first thing we can say is that the set of powers, I'm sorry, I didn't say, sorry guys, I missed one other thing. It's a monopolynomial of degree n. Give ourselves a number n. That's the degree of the set. So with that in mind, the set 1 alpha squared up to alpha n minus 1 is a basis of R alpha over R. Okay, I'm just going to verbally explain what I mean by that. Now, R is not assumed to be a field. So this R alpha is not a vector space in general. So what do we mean when we say a basis? Well, that's actually kind of complicated in general. But in this case, what we mean is that this is linearly independent and they span this group. In other words, if I take linear combinations of this over the ring, not the field, then I'll get all of the elements of R alpha from just these things. That's what I mean. So it's almost the same definition. However, some of the theorems are not available. Rank nullity, just maybe a little more. There's still a rank nullity actually, but you have to make some assumptions on that. Okay, So now, addition of two linear combinations, these guys. Gordon says this, and I'll just repeat it. It's just vector addition. In other words, it's just you add the coefficients, is what it's saying. Add coefficients. That's what it is. So what he's trying to do here is he's trying to talk about this ring and say, how do I manipulate elements? Saying, well, first of all, what are the elements of this ring? They're combinations of these guys with coefficients in R. How do I add them? Just add the coefficients. How do I multiply them? Well, that's C. For C, multiplication works as follows. So I'll just write down what he's got. It says, okay, so we have two elements, beta 1 and beta 2 in our alpha. And G1 of X and G2 of X are in R of X, so that beta 1 equals G of alpha, G1 of alpha, and beta 2 equals G2 of alpha. Basically, when you write G1 and G2, you're finding some coefficients. Okay, well, one thing we have with polynomials is we have our division algorithm. So we can divide the product of G1 and G2 by F, since F is monoid, by division algorithm. Divide 1 of X, 2 of X by F, and F of X, Q of X plus the remainder. And then the statement is beta 1, beta 2 with R. That's how you multiply. It's a little complicated, but it's not too bad. So what do I mean by that? Why is it not too bad? Well, let's say you have two elements. By part A, what you're saying is that you can write beta 1 and beta 2 as some combination of these. Once you do that, you're finding G1 and G2. Just substitute, make alpha X, right? Polynomial X. Then you can take the product and you can divide by F. Find a remainder, put an alpha, and you get the product. Let me just prove A. I'll let you look. I don't know if you can prove this section. How do we prove A? Prove linear independence. What do you guys think? Suppose we have some relation. What do we need to show? Get the CIs or not?
That the only solution is that the C is equal to 0.
Right, but all of them are zero. So how will we do that? Let's start with something. Let's let g of x. This looks a lot like a polynomial. Let g of x be the polynomial of these coefficients. Then g of x bar. Whose class of this? R of x. This quotient equal to alpha. Alpha is x in this quotient. When we look back up here, we're letting R alpha denote this ring, where alpha would take x to be alpha. Yeah.
G of x plus G of x, so we just
Yes. So what is the bar I'm writing? It's not complex conjugation or anything like that. I'm just writing it to denote the class. So when I look in it, when I look inside of this quotient ring, what are the elements of this? Well, we've got this ideal here. And the quotient ring includes this quotient group. We just take the additive group part. We just start thinking of cosets, additive cosets of this sub of the ID as a ring structure, as we saw last week. The point is I want to distinguish an element of this ring from its class in the quotient. So I'll put a bar over it just to denote and talking about this quotient. So but this bar is saying, okay, we're in this quotient, but x in this quotient is alpha. So I'll put in alpha here and I'll get this expression. And that will equal g of alpha, which is 0. That means that if something is 0 in the quotient, that means that the thing that you're using as your representative must be in the ID. Must be in that subgroup or sub ideal that you're quotienting out by. Okay, so now someone can tell me, or at least what I have to say. So what's going on? It was pointed out we want all of the coefficients to be 0. Why are they all 0? But this is a principal idea. Multiples f of x is what again? Polynomial of degree. The multiple of a monic polynomial of degree. Sure, sometimes. But I can multiply by x, right? I multiply x cubed by x to the 4th. 4, right? I multiply x cubed by any polynomial and get x. A polynomial, not a rational. Multiply polynomials together, and one of them is monic, then the leading terms will multiply and you get a higher leading term, right? Or at least this, it can be a constant multiplied by the same degree of the leading. You can't lower the degree because you don't have x in So these guys, all of the non-zero guys in here have degree that is greater than or equal to n. A G has degree less than n minus 1 at most. The only way G can be in here is if G is 0. Either G 0 I just want to say our degree of G of x is greater than or equal to the degree of f, which is n. But this doesn't apply. Okay. So it's linearly, these guys are linearly dependent. Do they span? I want to show that they also span. I'll show. If beta is an element of our alpha, beta to, well, some expression like this. Something. Why is that? So remember what R alpha is. R alpha is this quotient. This. Well, beta is an element of R alpha. We're assuming that. This is this quotient by definition. What that implies, the beta is equal to some a class of some polynomial. Let's call it G of x. For some G. Okay. So problem here. And we wrote this out, and since x is alpha, we would get an expression that looked a lot like this. However, we didn't say anything about the degree of G, so it could keep on going, right? It could go up to some alpha to the end. We could have a problem. We want to show that that we can find some polynomial whose degree is less than n. What can we do? Remember, we're killing f here. Only one trick in this book. Well, not in this little book, but in this game, there's only one trick that we use over and over again. We use it a lot when we're dealing with integers, a lot when we're dealing with polynomials. That's this division. So what we want to say is, okay, well, we've got a polynomial G, and its degree is big, potentially. We want it to be less than the degree of some polynomial f. Well, let's divide and get a remainder. That will have degree less than that. So by division algorithm, and remember, we have a monic. A key point is that f is monic. Otherwise, we can't apply this. Otherwise, and it's not true. Also. So that's another issue. If the g of x is equal to f of x cube of x plus r of x, where r has degree less than n. Less than or equal to less than. Okay. So I said that beta equals g of x class. That's the same as g of alpha. I mean, x is alpha in the quotient. Now I just evaluate, put alpha into everything. Beta equals g of alpha. That equals f of alpha. And q of alpha plus r of alpha. But f of alpha, the whole point of this whole thing that we're doing here is we want to kill a relation. And we want f of alpha to equal 0, right? The whole definition here is based on this equation. We want to enlarge our ring, adjoin an element so that that element satisfies one polynomial relation. So f of alpha is 0. This is r of alpha. But now r has degree less than n. So r can be written this way. Get beta is equal. Make sense? Or less? Or less than more. Okay. All right, this is a game that algebraists have been playing for hundreds of years, and mathematicians, right? The existence of the complex numbers is based on this game. Right? Saying people didn't like these, call it imaginary number I. Well, I was an imaginary number because I is something you would join onto the real, satisfying this single relation, I squared equals -1. You build a new algebra from that. And all of a sudden, over 100 years or so, it gets taken as like, okay, well, this is something real. Like, this is something important. But this game can be played with any ring. And we can learn a lot about these algebras if we just sort of take them abstractly and work with them. Another ring, the last couple of minutes, which is a funny kind of ring, is the Eisenstein integers. Eisenstein was a great algebraist and also a great complex geometer. Gauss, like so Eisenstein maybe asked the question, like, if we instead of, so there's the Gaussian integers, which is you just join on top of the integers, you put I in. And I is this x squared. Gaussian integers are something you're more familiar with, probably. These are Z adjoined I. And if you look at the lattice that you get, complex plane, it's a square lattice. Right, here's I, here's 1, I plus 1. This is the interesting thing is that, okay, we can see this as a lattice, a sub-vector space of R2, but it has a multiplication. There's like more structure to this algebra than just addition, just translation. And I acts as this rotation, this rigid isometry. Like multiply. So there is the Eisenstein integers are sort of the other highly symmetric lattice. There's Z of x, I mean, one way, Z of x over x squared. That's x. This, of course, is Z of x squared plus 1. Now we change the polynomials. And here you wrote Z of I for the Gaussians. Here you write Z of omega. Well, I don't know. You don't have to write it Z of omega. So this is just one of the common notations. For omega is a root of this polynomial, and this is the third cyclotomic polynomial. But the roots are the third root of unity. By I. 3. Or That's the square root of 3 times I. What you'll see if you draw this out, of course, is, okay, I put it in my notes the amount of times I want to replicate it. You see this hexagonal lines, a bathroom tile lines. Right? So this lattice is, yeah, as I said, this is a lattice that you can rotate by 3, and you'll get an isometry there. But that rotation is occurring as a complex multiplication. So you get some ring structure on the lattice, with the lattice being the set of intersections of these lines. Hexagonal lattice. Anyway, maybe I'll say a little bit more about isoside integers next time, but then we'll move on to product